Picture this. You're standing on a vast ice sheet stretching endlessly to the horizon, watching massive glaciers carve through ancient valleys like slow-motion bulldozers. The world is locked in an ice age that's lasted for tens of thousands of years. Then, suddenly, the climate begins to warm. The ice starts retreating. Life begins to flourish again across the northern continents. For over 1,000 years, this warming trend continues, and it seems like the planet is finally emerging from its frozen slumber. But then, in what feels like the blink of an eye in geological terms, everything changes. The warming stops. The cold returns with a vengeance. And for the next 1,200 years, the Earth plunges back into near Ice Age conditions so abruptly and so severely that it rewrites the entire story of human civilization, megafauna extinction, and planetary climate systems forever. This isn't science fiction. This is the Younger Dryas, one of the most dramatic and mysterious climate events in Earth's recent history. And what makes it even more fascinating is that mainstream science still can't fully explain what caused it. Hello, and welcome back. I'm absolutely thrilled to dive into this topic with you, because the Younger Dryas isn't just another climate event buried in geological textbooks. It's a story that connects cosmic catastrophe theories, ancient civilizations, mass extinctions, and cutting-edge archaeological discoveries in ways that challenge everything we thought we knew about the past 12,000 years of human history. Now, before we get too deep into the mystery, let me set up what we're dealing with here. The Younger Dryas period lasted from approximately 12,800 to 11,700 years ago. That might sound like ancient history, but in climate terms, this event was incredibly recent. We're talking about something that happened well within the time frame of modern humans, during a period when sophisticated hunter-gatherer societies were already established across multiple continents. What makes the Younger Dryas so remarkable isn't just its timing, it's the speed and severity of the climate change it represents. We're talking about average temperatures dropping by as much as 15 degrees Celsius in some regions, and this happening over periods as short as a few decades. To put that in perspective, the climate change we're experiencing today, which feels dramatic and rapid to us, is happening at a snail's pace compared to what occurred during the Younger Dryas transition. The event gets its name from a small Arctic flower called Dryas octopetala, which thrived in the cold conditions that returned during this period. When scientists first discovered evidence of this climate reversal in Scandinavian pollen records, they noticed that the pollen of this cold-loving plant appeared in layers that should have contained warm climate vegetation. It was as if someone had rewound the climate clock by thousands of years. But here's where things get really interesting. The Younger Dryas wasn't just about temperature drops and advancing ice sheets. This period coincides with some of the most significant changes in human history and Earth's biological systems that we know of. First, let's talk about the megafauna extinctions. During the Younger Dryas period, North America lost an estimated 35 genera of large mammals. We're talking about woolly mammoths, mastodons, giant ground sloths, saber-toothed cats, American lions, short-faced bears, and dozens of other species that had survived multiple previous ice ages but couldn't make it through this particular climate event. South America lost even more species during this same time frame. What's puzzling about these extinctions is their selectivity. Large mammals were hit hardest, while smaller animals and most plant species survived relatively well. This pattern doesn't match what we'd expect from a gradual climate change, or even a typical ice age transition. It looks more like the aftermath of a sudden, catastrophic event that specifically impacted large-bodied animals and their ecosystems. Now, here's where the human story becomes absolutely crucial. The Younger Dryas period marks the end of the Clovis culture in North America, one of the most widespread and successful hunting societies of its time. Clovis people were known for their distinctive spear points and their ability to hunt megafauna across vast territories. Archaeological evidence shows that Clovis sites appear across North America around 13,000 years ago, and then they disappear from the archaeological record right at the beginning of the Younger Dryas. But the human story doesn't end there. The Younger Dryas also corresponds with the emergence of agriculture in multiple locations around the world. The transition from hunting and gathering to farming, which archaeologists call the Neolithic Revolution, begins in earnest during and immediately after this climate event. Some researchers argue that the harsh conditions of the Younger Dryas actually forced human societies to develop agriculture as a survival strategy. In the Middle East, we see the first permanent settlements and the beginnings of crop cultivation appearing right around this time. The famous site of Göbekli Tepe in Turkey, which features massive stone monuments that predate Stonehenge by thousands of years, was constructed during the final centuries of the Younger Dryas period. This suggests that even during these harsh climate conditions, some human societies were developing increasingly complex social and religious systems. So we have this perfect storm of events: dramatic climate change, mass extinctions, the disappearance of major hunting cultures, and the emergence of agriculture and monumental architecture. The question that's been driving researchers crazy for decades is, what could have caused all of these changes to happen simultaneously? The traditional explanation, which you'll find in most geology textbooks, focuses on changes in ocean circulation patterns, particularly in the North Atlantic. The theory goes like this: as the massive ice sheets of the last ice age began to melt, enormous amounts of fresh water poured into the oceans. This fresh water disrupted the normal circulation of ocean currents, particularly the Gulf Stream system that brings warm water northward along the Atlantic coast. When this circulation system shut down or slowed dramatically, it caused temperatures to plummet across the North Atlantic region and beyond. The climate system essentially got stuck in a feedback loop, where colder temperatures led to more ice formation, which reflected more sunlight back to space, which caused even more cooling. This explanation makes sense for the regional climate changes we see in places like Northern Europe and Eastern North America. But it has trouble accounting for the global nature of many Younger Dryas effects, and it doesn't easily explain the sudden onset of the cooling or the precise timing of the megafauna extinctions. That's where alternative theories come into play, and this is where our story gets really fascinating. Over the past few decades, a growing number of researchers have proposed that the Younger Dryas wasn't caused by gradual changes in ocean circulation, but by a sudden catastrophic event. Specifically, they argue that around 12,800 years ago, Earth was struck by fragments of a disintegrating comet. This theory, known as the Younger Dryas Impact Hypothesis, suggests that multiple comet fragments exploded in the atmosphere over North America, creating massive fireballs that incinerated forests across the continent, triggered widespread wildfires, and threw enormous amounts of dust and debris into the atmosphere. The immediate effects would have been devastating. Flash, frozen mammoths found with undigested food in their stomachs, massive die-offs of large animals, and the disruption of human societies across the continent. The longer-term effects would have been even more dramatic. The dust and smoke from the impacts and subsequent fires would have blocked sunlight, causing rapid cooling. The impacts might have also destabilized ice sheets, causing massive freshwater pulses into the oceans that disrupted circulation patterns. In other words, the cosmic impact could have triggered all of the other changes that traditional theories attribute to gradual processes. Evidence for this impact theory has been mounting over the years. Researchers have found elevated levels of platinum and other rare metals in sediment layers dating to the beginning of the Younger Dryas. They've discovered microscopic diamonds and other materials that form under extreme pressure and temperature conditions. They've identified what appear to be impact craters and shock metamorphosed minerals in deposits of the right age. Perhaps most intriguingly, they've found evidence of massive wildfires and sudden changes in vegetation patterns that occurred right at the Younger Dryas boundary. Some sites show layers of charcoal and burned material so extensive that they suggest continent-wide conflagrations. But the impact theory remains controversial. Critics argue that many of the proposed evidence markers could have been formed by other processes, and they point out that no confirmed impact crater of the right age and size has been definitively identified. The debate continues to rage in scientific journals and conferences, with new evidence being presented on both sides. What makes this debate so compelling is that it's not just about ancient climate change. It's about how we understand catastrophic change in general, and how sudden, dramatic events can reshape entire planetary systems. If the impact theory is correct, it means that relatively small cosmic events can have massive, long-lasting consequences for life on Earth. The implications extend far beyond academic geology and archaeology. If comet impacts can trigger rapid climate change and mass extinctions, what does that mean for our understanding of other extinction events in Earth's history? What does it tell us about the stability of our current climate system? And perhaps most importantly, what does it suggest about the vulnerability of human civilization to cosmic threats? These questions become even more urgent when we consider that the Younger Dryas event may not have been unique. Some researchers argue that similar cosmic impact events may have occurred multiple times throughout human history, causing the collapse of ancient civilizations and triggering periods of rapid cultural and technological change. The story of the Younger Dryas is still being written. New archaeological discoveries continue to shed light on how human societies responded to this dramatic climate event. Advanced dating techniques are helping researchers pinpoint exactly when different changes occurred and in what sequence. And improved climate models are helping scientists understand how cosmic impacts might translate into long-term environmental changes. What's particularly fascinating about ongoing Younger Dryas research is how it's forcing us to reconsider the entire timeline of human development. For decades, archaeologists operated under the assumption that complex societies only emerged gradually after the development of agriculture, which supposedly began around 10,000 years ago. But sites like Göbekli Tepe are shattering those assumptions. This massive stone complex in southeastern Turkey features intricately carved pillars, arranged in circles, some weighing up to 20 tons. The precision of the stonework and the sophistication of the carved reliefs depicting various animals suggest a level of social organization and technical skill that shouldn't have existed among hunter-gatherer societies. Yet radiocarbon dating places its construction firmly within the Younger Dryas period, when the climate was at its harshest. But here's what's really mind-bending about Göbekli Tepe. It appears to have been deliberately buried. Around 8,000 years ago, the entire complex was covered with tons of earth and rocks, preserving it perfectly until modern excavations began. Who would go to the enormous effort of burying such a magnificent monument? And why? Some researchers suggest that the burial was intentional preservation, perhaps carried out by people who knew that dangerous times were coming and wanted to protect their sacred site for future generations. Others propose that the burial represents a deliberate break with the past, a way for emerging agricultural societies to symbolically cover up their hunter-gatherer origins. Either way, the implications are staggering. If hunter-gatherer societies during the Younger Dryas were capable of creating monumental architecture on this scale, what else might they have accomplished that we haven't discovered yet? How many other sites remain buried under millennia of sediment and vegetation? This question becomes even more intriguing when we look at the global distribution of similar megalithic sites that date to the end of the Younger Dryas period. From the stone circles of Britain to the massive structures at Poverty Point in Louisiana, there seems to have been a worldwide flowering of monumental construction right around the time the climate was stabilizing after the Younger Dryas event. The pattern suggests something profound was happening to human consciousness and social organization during this period. Perhaps the trauma of surviving a global catastrophe led to new forms of religious expression and social cooperation. Or maybe the harsh conditions of the Younger Dryas actually accelerated human cultural evolution by forcing communities to develop more sophisticated organizational systems. The animal carvings at Göbekli Tepe provide another piece of this puzzle. The pillars feature detailed depictions of lions, bulls, snakes, scorpions, and various birds. Many of these animals are shown in aggressive or threatening poses, as if the monument was designed to commemorate or ward off dangerous creatures. Intriguingly, several of the species depicted went extinct at the end of the Younger Dryas period. This has led some researchers to propose that Göbekli Tepe and similar sites might actually be memorial complexes built to commemorate the mass extinction event that wiped out so many large animal species. If this interpretation is correct, it would mean that the people who built these monuments had direct cultural memory of the catastrophe that ended the Younger Dryas. The idea that ancient peoples preserved memories of catastrophic events in their monuments and myths isn't as far-fetched as it might initially seem. Oral traditions from indigenous cultures around the world contain remarkably detailed accounts of floods, fires from the sky, and periods when the sun was blocked by darkness. Many of these stories include specific details about animal extinctions and climate changes that match what we know about the Younger Dryas period. Take the flood narratives that appear in cultures across the globe. From the biblical account of Noah's flood, to the Mesopotamian epic of Gilgamesh, to Native American stories of world-ending deluges, these tales share common elements: sudden onset, divine or cosmic causation, the survival of only a few humans and animals, and the need to rebuild civilization afterward. Traditional scholarship has typically dismissed these as mythological accounts with no historical basis. But what if they're actually cultural memories of real events that occurred during the Younger Dryas period? The massive freshwater pulses that disrupted ocean circulation would have caused dramatic changes in sea level and precipitation patterns. Coastal areas would have been flooded, river systems would have changed course, and entire landscapes would have been transformed. From the perspective of the human societies living through these changes, it would indeed have seemed like the end of the world. The fact that similar stories appear in cultures that had no contact with each other suggests they might be preserving memories of the same global event. The implications of this possibility are profound. It would mean that human cultural memory extends much further back than previously thought, and that our ancestors were capable of preserving accurate information about catastrophic events across hundreds of generations. It would also suggest that the transition from the Paleolithic to the Neolithic wasn't gradual cultural evolution, but a response to specific historical trauma. This brings us to one of the most controversial aspects of Younger Dryas research: the possibility that advanced human civilizations existed before the catastrophe and were largely destroyed by it. This idea challenges the fundamental assumption of linear progress that underlies most historical thinking. The evidence for pre-Younger Dryas advanced societies is circumstantial but intriguing. We have sophisticated cave paintings dating back 40,000 years that demonstrate remarkable artistic skill and possibly astronomical knowledge. We have evidence of long-distance trade networks and complex tool technologies that suggest higher levels of social organization than traditionally assumed for Paleolithic societies. Most provocatively, we have anomalous archaeological sites that seem to predate the supposed development of complex societies. Underwater ruins off the coasts of various continents show architectural features that would require sophisticated engineering knowledge. Some of these sites are now submerged under hundreds of feet of water, suggesting they were built when sea levels were much lower during the last ice age. The famous Bimini Road in the Bahamas, the underwater structures off Yonaguni in Japan, and the submerged ruins near Alexandria in Egypt all share certain characteristics. Massive stone blocks arranged in geometric patterns, evidence of advanced quarrying and transportation techniques, and locations that would have been above water only during the Ice Age or shortly after. Mainstream archaeology remains skeptical of claims for pre-Younger Dryas civilizations, arguing that the underwater structures are natural geological formations and that there's insufficient evidence for complex societies before the Neolithic period. But the accumulating evidence is becoming harder to ignore, especially as underwater archaeology techniques improve and more sites are discovered. The possibility of lost civilizations connects directly to the cosmic impact theory of the Younger Dryas. If comet fragments did indeed strike the Earth 12,800 years ago, the effects would have been catastrophic for any advanced societies that existed at the time. Coastal cities would have been destroyed by tsunamis, agricultural systems would have been disrupted by climate change, and the knowledge bases of entire civilizations could have been lost in a single generation. The survivors would have been forced to start over under harsh conditions, using whatever knowledge and skills they could preserve through oral tradition and scattered artifacts. This scenario would explain why we see such a dramatic flourishing of monumental architecture and complex societies immediately after the Younger Dryas ended. These weren't new developments, but the rebuilding efforts of civilizations that were trying to reconstruct what had been lost. This interpretation also explains some puzzling aspects of early post-Younger Dryas societies. Why did agriculture appear simultaneously in multiple locations around the world, using different crops and techniques but showing similar levels of sophistication? Why do the earliest known cities show evidence of advanced urban planning and engineering from their very beginnings? Why do megalithic monuments from this period demonstrate mathematical and astronomical knowledge that supposedly took centuries to develop? If these societies were rebuilding rather than building from scratch, their rapid advancement makes much more sense. They weren't starting from zero, they were working from fragmented memories of more advanced predecessor civilizations, trying to piece together lost knowledge while adapting to new environmental conditions. The cosmic connection adds another layer of complexity to this story. If Earth is periodically bombarded by comet debris from specific sources in the outer solar system, then the Younger Dryas event might be part of a longer cycle of catastrophes that have repeatedly disrupted human development. Some researchers have identified potential earlier impact events that correlate with other periods of rapid climate change and cultural disruption. The possibility that our planet moves through debris fields on predictable schedules raises uncomfortable questions about the stability of human civilization and our ability to survive future encounters with cosmic threats. This cyclical catastrophe theory would explain why so many ancient cultures developed sophisticated astronomical observation systems and why their mythologies are filled with stories of recurring world-ending events. Perhaps our ancestors were trying to predict and prepare for the next catastrophe based on their understanding of celestial cycles. The search for answers continues as new technologies allow researchers to explore previously inaccessible evidence. Satellite archaeology is revealing hidden structures buried under vegetation and sediment. Advanced dating techniques are providing more precise chronologies of when different changes occurred. Climate modeling is helping scientists understand how cosmic impacts might have triggered the complex chain of environmental changes we see in the geological record. Each new discovery adds another piece to the puzzle, but also raises new questions about the true history of human civilization and Earth's vulnerability to cosmic catastrophes. The Younger Dryas isn't just ancient history, it's a window into understanding how sudden, dramatic changes can reshape entire planetary systems and the life they support. What makes this even more compelling is the growing body of evidence that suggests the Younger Dryas impact wasn't a single event, but rather a series of impacts that occurred over several years or even decades. This would explain why the environmental changes were so severe and long-lasting, and why the effects were felt across such a wide geographic area. Recent studies have identified what researchers call the Younger Dryas boundary layer, a distinct geological marker found at sites across North America and Europe. This layer contains an unusual mixture of materials that shouldn't naturally occur together: microscopic diamonds that form only under extreme pressure, metallic spherules that appear to have been created by intense heat, and elevated concentrations of platinum, and other elements that are rare in Earth's crust but common in asteroids and comets. But here's where it gets really fascinating. The boundary layer isn't uniform across all sites. In some locations, it's thick and contains abundant impact markers. In others, it's thin or even absent altogether. This patchy distribution suggests that the impacts weren't evenly spread across the planet, but rather concentrated in certain regions while leaving others relatively untouched. This pattern has led researchers to propose what they call the cosmic shotgun model of the Younger Dryas catastrophe. Instead of one massive impact, Earth may have been struck by hundreds or thousands of smaller fragments from a disintegrating comet, creating a devastating but geographically uneven pattern of destruction. The implications of this model are staggering when we consider human populations at the time. Archaeological evidence suggests that the highest concentrations of Clovis sites in North America correspond almost perfectly with the areas where the impact markers are most abundant. This isn't coincidence. It suggests that the cosmic impacts specifically targeted the regions where advanced hunting societies were most well established. The timing becomes even more significant when we look at what was happening in other parts of the world during this same period. While North America was being devastated by impacts and their aftermath, other regions were experiencing different but equally dramatic changes. In Europe, the advancing ice sheets were forcing populations southward. In Asia, shifting monsoon patterns were transforming vast areas from grasslands into deserts. But perhaps most intriguingly, some regions seem to have been relatively protected from the worst effects of the Younger Dryas climate changes. Parts of the Middle East, certain areas of South America, and isolated pockets in other continents maintained more stable conditions even as the global climate system was in chaos. These refugia, as researchers call them, may have served as preserves for both human populations and the knowledge systems they carried. While civilizations in impact zones were being destroyed, communities in protected areas could have continued developing their technologies and social systems. When the climate finally stabilized at the end of the Younger Dryas, these surviving groups would have been positioned to rapidly expand into the devastated regions, bringing with them whatever knowledge and skills had been preserved during the catastrophe. This refugia model helps explain one of the most puzzling aspects of post-Younger Dryas archaeology: the sudden appearance of sophisticated technologies and social systems in regions that show no evidence of gradual development leading up to them. Instead of slow evolution from simple to complex, we see what appears to be the arrival of fully formed cultural packages that include advanced tool-making techniques, architectural knowledge, and complex symbolic systems. The genetic evidence adds another layer to this story. DNA studies of modern populations reveal patterns that are difficult to explain through gradual migration and population growth. Instead, they suggest periods of rapid population expansion from specific source regions, followed by mixing with local populations that had survived in isolated refugia. These genetic bottlenecks and expansions correspond remarkably well with the timing of the Younger Dryas event and its aftermath. It's as if entire populations were compressed into small survival zones during the catastrophe, then rapidly spread out again once conditions improved, carrying with them whatever cultural and technological knowledge had been preserved. The preservation of knowledge during catastrophic periods brings us to one of the most intriguing aspects of Younger Dryas research: the possibility that our ancestors developed specific strategies for surviving global catastrophes. If cosmic impacts or other planetary-scale disasters occurred repeatedly throughout human history, then successful populations would have been those that learned to prepare for and survive such events. This preparation might have included the development of knowledge preservation systems that could survive the destruction of normal social structures. Oral traditions, monument-based information storage, and the training of specialist knowledge keepers could have served as backup systems for maintaining critical information across catastrophic periods. The megalithic monuments that appear worldwide at the end of the Younger Dryas might represent exactly this kind of knowledge preservation system. Rather than simple religious or ceremonial structures, they could have been designed as information storage and transmission devices, encoding astronomical, mathematical, and practical knowledge in stone forms that could survive, even if the societies that built them were destroyed. This interpretation gains support from the sophisticated astronomical alignments found at many of these sites. Göbekli Tepe's pillars are aligned to specific star positions. Stonehenge tracks solar and lunar cycles with remarkable precision. The pyramids of Giza align to cardinal directions and specific stellar configurations. These aren't accidental features. They represent deliberate attempts to encode astronomical knowledge in permanent form. But the encoded information goes beyond simple star maps. Many megalithic sites incorporate mathematical relationships that weren't supposedly discovered until thousands of years later. The golden ratio, pi, and complex geometric principles appear in the proportions and layouts of monuments built by societies that had no written mathematics. This suggests that the knowledge being preserved wasn't primitive or intuitive, but rather represented sophisticated understanding of natural principles that took advanced civilizations considerable time to develop. The monuments weren't just marking the beginning of complex societies, they were preserving the remnants of even more advanced predecessors. The question of why this knowledge needed to be preserved in stone brings us back to the cyclical nature of cosmic catastrophes. If our ancestors understood that Earth periodically encounters dangerous debris fields, they would have known that their civilizations were vulnerable to destruction at predictable intervals. The astronomical alignments at megalithic sites might not just be calendars or ceremonial markers. They could be warning systems designed to predict when the next dangerous period would arrive. By tracking the positions of stars and planets, ancient astronomers could have calculated when Earth would again pass through the debris field that caused the Younger Dryas catastrophe. This predictive knowledge would have been incredibly valuable for long-term survival planning. Communities that knew a catastrophic period was approaching could have prepared by building underground shelters, stockpiling resources, and training specialist groups to preserve essential knowledge and skills. The evidence for such preparation systems appears in archaeological sites around the world. Underground complexes like Derinkuyu in Turkey could have served as catastrophe shelters rather than simple storage areas. The elaborate tunnel systems found beneath many ancient cities might have been designed to protect populations during periods of surface danger. Even more intriguingly, some of these underground complexes show evidence of sophisticated life support systems, ventilation shafts, water storage and distribution networks, and spaces for housing large numbers of people for extended periods. These features suggest they were designed for long-term occupation during dangerous surface conditions. The timing of when these underground systems were built adds another piece to the puzzle. Many date to periods that correspond with known or suspected cosmic impact events. It's as if our ancestors were following a playbook for catastrophe preparation that had been developed through multiple previous experiences with planetary disasters. This cyclical preparation model would also explain the recurring themes in mythology about gods or advanced beings who periodically return to Earth. Rather than supernatural entities, these stories might preserve cultural memories of survivors from previous catastrophic cycles who retained advanced knowledge and used it to help rebuild civilization after each disaster. The gods in these stories often have specific characteristics that match what we might expect from catastrophe survivors. They possess advanced knowledge of astronomy, mathematics, and engineering. They appear suddenly in regions that had previously shown little cultural development. They establish new technologies and social systems, and they eventually withdraw or disappear, leaving behind only monuments and memories. These patterns appear in mythologies from around the world with remarkable consistency. The Mesopotamian Anunnaki, the Egyptian Neteru, the Hindu Devas, and the Mesoamerican feathered serpent traditions all describe similar figures who bring civilization to humanity, establish great works, and then depart with promises to return at some future time. If these stories preserve memories of actual historical events rather than pure mythology, they would represent an incredibly sophisticated information preservation system. Complex historical knowledge would have been encoded in narrative form that could be transmitted across generations, even without written language. The cyclical return theme in these mythologies takes on new significance in light of what we now know about cosmic debris fields and orbital mechanics. If Earth does indeed encounter dangerous regions of space on predictable schedules, then the return of the gods might represent the recurring pattern of catastrophe, survival, and rebuilding that has shaped human civilization for far longer than we previously realized. This brings us to perhaps the most unsettling implication of Younger Dryas research, the possibility that we are currently approaching another dangerous period in the cosmic cycle. Some researchers have identified astronomical indicators that suggest Earth may be entering or approaching a debris field similar to the one that caused the Younger Dryas catastrophe. The evidence includes increased meteor activity, anomalous atmospheric phenomena, and changes in cosmic ray flux that match patterns seen in ice core data from the Younger Dryas period. While these indicators are still preliminary and highly debated, they raise important questions about our preparedness for potential cosmic threats. Unlike our ancestors, modern civilization is highly centralized and dependent on complex technological systems that would be extremely vulnerable to the kinds of impacts and environmental changes that occurred during the Younger Dryas. A single large impact or a series of smaller ones could disrupt global communications, transportation, and power systems, leading to societal collapse even in regions not directly affected by the impacts themselves. The irony is that while we have much more sophisticated technology than previous civilizations, we may actually be less resilient to catastrophic events. Our ancestors lived in decentralized communities with diversified survival skills and strong oral knowledge preservation systems. Modern populations are concentrated in cities and dependent on specialized systems that most people don't understand or know how to maintain. This vulnerability makes the lessons of the Younger Dryas more than just academic curiosities. Understanding how previous civilizations survived cosmic catastrophes might be essential for ensuring that our own civilization can survive similar future events. The research continues, with new discoveries constantly adding to our understanding of this pivotal period in human and planetary history. Advanced imaging techniques are revealing hidden archaeological sites that were buried during the Younger Dryas. Improved climate modeling is helping scientists understand the complex chain reactions that cosmic impacts can trigger in Earth's environmental systems. Perhaps most importantly, the growing recognition that cosmic catastrophes have played a major role in shaping human civilization is leading to increased attention to planetary defense systems and catastrophe preparedness planning. The lessons learned from studying the Younger Dryas aren't just about understanding the past, they're about protecting the future. The story of the Younger Dryas challenges us to reconsider our assumptions about the stability of civilization and our place in the cosmic environment. It reminds us that Earth is part of a dynamic solar system where catastrophic events are not just possible but inevitable over long time periods. But it also demonstrates the remarkable resilience and adaptability of human societies when faced with seemingly impossible challenges. The fact that we're here to study these ancient catastrophes means that our ancestors found ways to survive and preserve their knowledge through the worst planetary disaster in recent history. Human ingenuity, careful preparation, and the preservation of essential knowledge allowed previous civilizations to survive the Younger Dryas catastrophe and rebuild afterward. The same qualities that enabled our ancestors to weather that crisis may be exactly what we need to face whatever cosmic challenges lie ahead in our own future. The Younger Dryas isn't just ancient history, it's a preview of the kinds of challenges that Earth and its inhabitants face on cosmic timescales. Understanding this pivotal period in our planet's history isn't just about satisfying scientific curiosity. It's about learning the lessons we need to ensure that human civilization can survive and thrive, regardless of what the cosmos throws our way. The survival strategies that emerged from the Younger Dryas catastrophe reveal something profound about human adaptability, but they also expose a troubling pattern that we're only now beginning to understand. As communities struggled to rebuild in the aftermath of the cosmic impacts, they didn't just develop new technologies and social systems, they fundamentally altered their relationship with the environment and with each other in ways that would shape the trajectory of human civilization for millennia to come. The archaeological evidence from immediate post-Younger Dryas sites tells a story of rapid innovation born from desperate necessity. Tool technologies that had remained relatively stable for thousands of years suddenly exploded into dozens of specialized forms. Hunting strategies shifted from targeting large megafauna to exploiting smaller, more diverse prey species. Most significantly, human societies began to actively manipulate their environments rather than simply adapting to them. This manipulation represents a crucial turning point in human evolution, not biological evolution, but cultural evolution. For the first time in our species' history, we began to systematically alter landscapes to suit our needs, rather than adjusting our behaviors to fit existing conditions. The domestication of plants and animals that characterizes the Neolithic Revolution wasn't just a gradual discovery of farming techniques. It was a coordinated response to a world where the natural systems that had supported human societies for tens of thousands of years had been fundamentally disrupted. But here's what makes this transition so fascinating and so troubling. The speed at which these changes occurred suggests they weren't discoveries made from scratch. Instead, they appear to represent the systematic implementation of knowledge that had been preserved through the catastrophe, possibly in fragmented form, and was being reassembled and applied as conditions allowed. The evidence for this preserved knowledge appears in the remarkable similarity of techniques that emerged simultaneously in regions that had no apparent contact with each other. The development of pottery, for instance, appears in the archaeological record at multiple locations around the world within a few centuries of each other, all dating to the period immediately following the end of the Younger Dryas. These weren't crude experimental attempts. They were sophisticated ceramic technologies that demonstrated advanced understanding of clay properties, firing techniques, and functional design principles. Similarly, the astronomical knowledge encoded in early post-Younger Dryas monuments reveals understanding of celestial mechanics that supposedly took centuries to develop through observation. Yet this knowledge appears fully formed in the earliest examples we can date. The implication is either that our ancestors were far more capable of rapid learning than previously assumed, or that they were working from knowledge bases that predated the catastrophe. The social implications of this rapid technological development are equally intriguing. The coordinated construction projects that produced megalithic monuments required sophisticated organizational systems, specialized labor divisions, and resource management capabilities that shouldn't have existed among small, scattered survivor populations. Yet, the evidence suggests that these complex social systems emerged almost immediately as environmental conditions stabilized. This pattern appears worldwide with remarkable consistency. In the Fertile Crescent, permanent settlements with evidence of social stratification and specialized crafts appear within centuries of the Younger Dryas ending. In China, complex pottery traditions and agricultural systems emerge during the same time frame. In the Americas, the first large-scale earthwork constructions date to this period, demonstrating organizational capabilities that required coordinated efforts by hundreds or thousands of people. The speed and sophistication of these developments challenged traditional models of cultural evolution that assume gradual progression from simple to complex systems. Instead, we see what appears to be the rapid reconstruction of complex societies, using knowledge and organizational principles that had somehow been preserved through the catastrophic period. This preservation of knowledge becomes even more remarkable when we consider the conditions that survivor populations would have faced during the Younger Dryas. The climate data shows that much of the inhabited world experienced conditions similar to those found today in the harshest Arctic environments. Food resources would have been scarce and unpredictable. Populations would have been small and scattered. Under such conditions, maintaining complex knowledge systems would have required extraordinary dedication and sophisticated preservation techniques. The oral tradition systems that accomplished this feat of knowledge preservation represent one of humanity's greatest intellectual achievements, yet they receive little recognition in standard historical accounts. These weren't simple storytelling traditions. They were precisely structured information storage and transmission systems capable of preserving technical, astronomical, and social knowledge across hundreds of generations of speakers. The sophistication of these systems becomes apparent when we analyze the mythological and religious traditions that emerged from post-Younger Dryas societies. Embedded within seemingly simple stories are remarkably accurate descriptions of astronomical phenomena, mathematical relationships, and practical knowledge that would have been essential for rebuilding complex civilizations. Take the flood narratives that appear in cultures worldwide. When analyzed carefully, these stories contain specific details about water behavior, geological processes, and survival techniques that demonstrate sophisticated understanding of environmental dynamics. They're not just morality tales or creation myths. They're technical manuals disguised as stories, designed to preserve essential knowledge in memorable narrative form. The astronomical knowledge embedded in these traditions is particularly striking. Many flood narratives include precise descriptions of celestial events, seasonal cycles, and navigation techniques that would have been crucial for coordinating activities across large territories. The fact that these details appear consistently in traditions from cultures that developed independently suggests they were preserving memories of actual astronomical knowledge rather than creating fictional accounts. But the preservation systems went beyond oral traditions. The megalithic monuments that appeared worldwide at the end of the Younger Dryas represent physical information storage systems that could preserve knowledge even if the societies that built them were destroyed. These structures encode mathematical relationships, astronomical alignments, and engineering principles in stone forms that remain readable thousands of years after their construction. The precision of this encoded information is staggering. The Great Pyramid of Giza, for instance, incorporates the mathematical constant pi in its proportions, demonstrates knowledge of Earth's dimensions and rotational properties, and aligns to stellar positions with astronomical precision. These aren't coincidental features. They represent deliberate attempts to preserve sophisticated mathematical and astronomical knowledge in permanent form. Similar encoding appears in megalithic sites worldwide. Stonehenge functions as a complex astronomical computer, capable of predicting eclipses and tracking celestial cycles. The stone circles of Scotland incorporate geometric principles that weren't supposedly discovered until the development of classical mathematics. The earthworks at Poverty Point in Louisiana demonstrate advanced understanding of surveying and construction techniques that rival modern capabilities. The global distribution of these encoded monuments suggests that knowledge preservation was a coordinated effort rather than isolated local developments. The consistency of mathematical relationships and astronomical principles across sites separated by thousands of miles and supposedly built by unrelated cultures indicates that they were part of a unified system for maintaining and transmitting essential knowledge. This coordination becomes even more remarkable when we consider that it was accomplished without written language or long-distance communication systems. The only way such consistency could have been maintained across vast distances and long time periods is through carefully structured training systems that produce specialists capable of accurately transmitting complex information through oral instruction and practical demonstration. These knowledge preservation systems reveal something profound about the cognitive capabilities of our post-Younger Dryas ancestors. They weren't primitive hunter-gatherers gradually discovering agriculture and basic crafts. They were sophisticated knowledge workers, implementing complex information systems under extraordinarily difficult conditions. The implications extend far beyond archaeology and ancient history. If human societies 12,000 years ago were capable of preserving and transmitting complex technical knowledge through global catastrophes, what does that tell us about our own capabilities and vulnerabilities? Modern civilization has become increasingly dependent on centralized information storage systems that are potentially more fragile than the oral and monumental preservation systems used by our ancestors. Digital storage media degrade rapidly without maintenance. Written records can be destroyed by fire, flood, or simple neglect. Even our most important technical knowledge exists primarily in forms that require complex technological infrastructure to access and interpret. In contrast, the information preservation systems developed by post-Younger Dryas societies were designed for resilience. Oral traditions could be maintained by small groups of people without any technological support. Monument-based encoding could preserve information for thousands of years without maintenance. These systems were specifically designed to survive the kinds of catastrophic disruptions that could destroy centralized storage systems. The robustness of ancient knowledge preservation systems becomes particularly relevant when we consider the possibility that cosmic catastrophes occur on predictable cycles. If Earth periodically encounters dangerous regions of space, then the ability to preserve essential knowledge through catastrophic periods isn't just historically interesting. It's a survival skill that may be essential for long-term human survival. This brings us to one of the most disturbing aspects of current Younger Dryas research. Some scientists have identified indicators that suggest we may be approaching another period of increased cosmic danger. These indicators include changes in cosmic ray flux, increased meteor activity, and unusual atmospheric phenomena that match patterns found in ice core data from catastrophic periods. While these observations are still preliminary and highly debated, they raise important questions about our preparedness for potential cosmic threats. Unlike our ancestors, who developed sophisticated systems for surviving and recovering from global catastrophes, modern civilization has become increasingly vulnerable to the kinds of disruptions that cosmic impacts could cause. Our technological systems are highly interconnected and centralized, making them vulnerable to cascading failures that could result from relatively localized impacts. Our populations are concentrated in urban areas that would be difficult to evacuate quickly. Most importantly, our essential knowledge is stored in forms that require complex technological infrastructure to access, making it potentially inaccessible if that infrastructure is damaged. The contrast with post-Younger Dryas survival systems is striking. Our ancestors developed decentralized, resilient systems that could function under the most difficult conditions. They created multiple backup systems for preserving essential knowledge. They maintained diverse skill sets within their communities, rather than relying on narrow specialization. They designed their settlements and social systems to be adaptable rather than optimized for specific conditions. These weren't primitive responses to harsh conditions. They were sophisticated strategies for long-term survival under uncertain circumstances. The fact that these systems successfully preserved complex knowledge and technological capabilities through the worst global catastrophe in recent history demonstrates their effectiveness. The lessons from this analysis aren't just academic. They suggest specific strategies that modern societies could adopt to increase their resilience to catastrophic events. Decentralizing critical infrastructure, developing diverse local capabilities, creating robust information preservation systems, and maintaining knowledge of essential survival skills could significantly improve our chances of surviving and recovering from global disruptions. But implementing such strategies would require fundamental changes in how modern societies organize themselves and think about risk. Our current systems are optimized for efficiency under stable conditions rather than resilience under catastrophic conditions. Shifting toward more resilient systems would require accepting some inefficiency in exchange for greater long-term survival probability. The Younger Dryas research also highlights the importance of maintaining awareness of cosmic threats and developing planetary defense capabilities. Unlike our ancestors, who could only prepare for and respond to cosmic impacts, modern technology potentially gives us the capability to detect and deflect dangerous objects before they reach Earth. However, developing effective planetary defense systems requires long-term commitment and international cooperation on a scale that has rarely been achieved in human history. The fact that cosmic catastrophes occur on timescales much longer than typical political and economic planning horizons makes it difficult to maintain focus on these threats. The example of post-Younger Dryas societies suggests that successful long-term survival planning requires cultural systems that can maintain focus on rare but catastrophic threats across many generations. The astronomical knowledge preservation systems they developed served this function, maintaining awareness of cosmic cycles and potential threats across thousands of years. Modern equivalents of such systems might include dedicated institutions for monitoring cosmic threats, educational programs that maintain public awareness of these risks, and international agreements that ensure continuity of planetary defense efforts across changes in government and economic conditions. The scientific study of the Younger Dryas continues to reveal new aspects of this pivotal period in human and planetary history. Advanced analytical techniques are providing more detailed information about the timing and sequence of events during the catastrophe. Improved archaeological methods are uncovering evidence of how human societies responded to and recovered from the crisis. Perhaps most importantly, the growing recognition that cosmic catastrophes have played a major role in shaping human civilization is leading to increased attention to these threats in scientific and policy communities. The lessons learned from studying how our ancestors survived the Younger Dryas catastrophe are being applied to modern discussions of planetary defense and catastrophe preparedness. The story of the Younger Dryas ultimately demonstrates both human vulnerability and human resilience. It shows how quickly and dramatically cosmic events can disrupt planetary systems and human societies. But it also shows how human ingenuity, preparation, and knowledge preservation can enable survival and recovery even from the most severe catastrophes. The sophisticated response systems that emerged from the Younger Dryas catastrophe represent some of humanity's greatest achievements, yet they remain largely unrecognized in standard historical accounts. Understanding these systems isn't just about appreciating our ancestors' accomplishments. It's about learning the lessons we need to ensure that human civilization can survive whatever cosmic challenges may lie ahead. As we continue to unravel the mysteries of this remarkable period in Earth's history, we're not just satisfying scientific curiosity, we're developing the knowledge and perspective necessary to face an uncertain cosmic future with the same wisdom and resilience that carried our ancestors through the greatest catastrophe in recent planetary history. The Younger Dryas stands as both a warning and a promise. A warning that Earth and human civilization face real cosmic threats that can materialize with little warning and devastating consequences. But also a promise that human societies possess remarkable capabilities for survival, adaptation, and recovery when faced with seemingly impossible challenges. The question facing us now is whether we can learn from our ancestors' example and develop the wisdom, preparation, and resilience necessary to ensure that human civilization continues to thrive, regardless of what cosmic surprises the universe may have in store for us. The deeper we dig into post-Younger Dryas archaeological sites, the more we encounter evidence that challenges our most basic assumptions about the timeline of human development. Carbon dating from sites across multiple continents reveals a pattern that simply doesn't fit traditional models of gradual cultural evolution. Instead of seeing slow, incremental improvements in technology and social organization, we find quantum leaps that appear almost overnight in geological terms. Consider the megalithic structures that began appearing worldwide within centuries of the Younger Dryas ending. These weren't crude engineered monuments that demonstrate mastery of advanced stone piles thrown together by desperate survivors. They were precisioned mathematical principles, sophisticated understanding of astronomy, and organizational capabilities that required coordinated efforts by thousands of people working toward common goals. The engineering precision alone is staggering. At Pumapunku in Bolivia, stone blocks weighing over 100 tons were cut with tolerances that rival modern machining capabilities. The surfaces are so flat and the angles so precise that even today's engineers struggle to understand how such precision appears at sites from Easter Island to the was achieved without advanced tools. Similar Orkney Islands, all dating to the same general timeframe following the Younger Dryas, is the knowledge systems that these structures represent. Many, but it's not just the technical capabilities that are remarkable. It's like eclipses. The level of observational astronomy require complex celestial cycles, and predicting rare events of these sites function as sophisticated astronomical computers, capable of tracking to create such systems, would have taken centuries of careful record-keeping and mathematical analysis. Yet these capabilities appear fully formed in the earliest examples we can date. There's no archaeological evidence of gradual development from simple observations to complex calculations. Instead, we see immediate implementation of advanced astronomical knowledge that suggests the builders were working from established information systems rather than developing new ones from scratch. The implications become even more intriguing when we examine the global distribution of these astronomical knowledge systems. Sites separated by thousands of miles and supposedly built by unrelated cultures demonstrate remarkably consistent understanding of celestial mechanics and mathematical relationships. The same geometric principles, the same astronomical alignments, the same precision in construction appear worldwide during the same narrow time frame. This consistency is virtually impossible to explain through independent development. The only realistic explanation is that these sites were built by communities that shared common knowledge sources, either through direct contact or through preservation of information from earlier, more widespread civilizations. The mathematical sophistication embedded in these structures provides some of the strongest evidence for advanced predecessor civilizations. Complex geometric relationships that weren't supposedly discovered until the development of classical Greek mathematics appear encoded in monuments built thousands of years earlier by societies that had no known written mathematical systems. The golden ratio appears in the proportions of structures worldwide. Pi is incorporated into the dimensions of pyramids and stone circles. Advanced trigonometric relationships are built into the layouts of earthworks and ceremonial complexes. These aren't coincidences or approximations. They're precise implementations of mathematical constants that demonstrate deep understanding of geometric principles. Perhaps most remarkably, some of these monuments incorporate knowledge of Earth's physical properties that wasn't officially discovered until the modern era. The Great Pyramid's dimensions encode the planet's polar radius to remarkable accuracy. Stone earthworks in North America aligned to magnetic north with circles in Scotland incorporate measurements based on Earth's circumference, precision that suggests knowledge of the planet's magnetic field properties. This advanced knowledge appears not just in individual structures, but in coordinated networks of sites that function together as integrated systems. Ley line researchers have identified alignments between monuments that span continents, suggesting that the builders understood Earth's geometry on a global scale and deliberately positioned their structures to create functional relationships across vast distances. The energy properties associated with many of these sites add another layer of mystery to their purpose and construction. Sensitive instruments have detected unusual electromagnetic phenomena at megalithic locations worldwide. Ground-penetrating radar reveals subterranean chambers and passages that don't appear on surface surveys. Visitors frequently report altered states of consciousness, unusual sensory experiences, and other anomalous effects that suggest these sites interact with human neurology in ways we don't fully understand. Some researchers propose that these monuments were designed as consciousness-altering devices, using precise acoustic properties and electromagnetic fields to induce specific mental states in visitors. The architectural features that create these effects demonstrate sophisticated understanding of how environmental factors influence human perception and cognition. The acoustic properties are particularly striking. Many megalithic chambers exhibit resonant frequencies that match brainwave patterns associated with altered consciousness. Stone circles often amplify and focus sound in ways that create standing wave patterns capable of inducing trance states. The precision required to create these effects suggests the builders understood principles of acoustics and neurology that we're only beginning to rediscover. These consciousness-altering properties may have served specific functions in knowledge preservation and transmission systems. If advanced information was encoded in ways that required altered states of consciousness to access, then the monuments could have functioned as interfaces between normal awareness and preserved knowledge systems. This interpretation gains support from ethnographic studies of indigenous cultures that maintain traditional knowledge transmission practices. Many of these cultures use specific acoustic environments, geometric visual patterns, and other environmental factors to induce states of consciousness that facilitate learning and memory. The techniques are remarkably similar to the effects produced by megalithic monuments, suggesting continuity of practices across thousands of years. The biological evidence for advanced post-Younger Dryas societies extends beyond archaeological artifacts to genetic and physiological indicators preserved in human populations. DNA studies reveal patterns of rapid population expansion and mixing that correspond to the time frame when complex monuments were being constructed. These patterns suggest coordinated movement of large numbers of people across vast distances, indicating organizational capabilities far beyond what we'd expect from scattered survivor communities. Even more intriguingly, some populations show genetic markers that suggest adaptation to environmental conditions that no longer exist in their current territories. These adaptations appear to have developed over thousands of years, implying that the populations carrying them had been established in different environments for extended periods before migrating to their present locations. The cranial studies of human remains from early post-Younger Dryas sites reveal another puzzle. Some skulls show features that indicate exposure to environmental factors or nutritional conditions that don't match what we'd expect for the regions where they were found. The bone density, tooth wear patterns, and other indicators suggest these individuals had lived in environments with different climate conditions, elevation levels, or dietary resources than those available in their burial locations. These biological indicators point toward complex population movements and environmental adaptations that imply far more sophisticated social organization and resource management than traditional models of post-catastrophe societies would predict. Instead of small, isolated groups struggling for survival, we see evidence of coordinated communities capable of long-distance travel, resource sharing, and environmental management across diverse territories. The agricultural systems that emerged during this period provide additional evidence of advanced knowledge application rather than gradual discovery. The domestication of multiple plant and animal species occurred simultaneously in regions worldwide, using techniques that demonstrate sophisticated understanding of genetics, ecology, and environmental management. The speed of these domestication processes challenges traditional models of agricultural development. Converting wild plants and animals into domestic varieties typically requires many generations of selective breeding and environmental manipulation. Yet the archaeological evidence shows that complex agricultural systems appeared within centuries of the Younger Dryas ending, suggesting that the knowledge and techniques required for domestication were already available to post-catastrophe communities. The diversity of crops and techniques that appeared simultaneously is equally puzzling. Different regions developed agriculture based on entirely different plant and animal species, yet the underlying principles and methods show remarkable consistency. This suggests that post-Younger Dryas communities were applying common knowledge systems to local environmental conditions rather than independently discovering agricultural techniques. The environmental management practices associated with these early agricultural systems demonstrate understanding of ecological principles that we're only beginning to appreciate today. Techniques for soil management, water conservation, and biodiversity preservation appear fully developed in the earliest agricultural sites we can identify. These practices weren't just effective for short-term food production, they were designed for long-term sustainability and environmental enhancement. Archaeological evidence shows that many early agricultural regions became more productive and ecologically diverse under human management than they had been in their natural states. The precision and sophistication of these environmental management systems suggest that post-Younger Dryas societies understood ecological relationships and environmental dynamics at a level that required extensive observation, experimentation over long time periods. Yet this knowledge appears to have been implemented immediately as agricultural systems developed, indicating that it was preserved from earlier periods rather than developed from scratch. The social organization required to implement such complex systems provides insight into the governmental and cultural structures that emerged from the Younger Dryas catastrophe. The coordinated construction projects, resource management systems, and knowledge preservation networks that characterize this period required sophisticated leadership structures and communication systems. Archaeological evidence from early post-Younger Dryas sites reveals social stratification and specialized roles that indicate complex hierarchical organization. But these weren't simple authoritarian systems based on force or resource control. Instead, they appear to have been merit-based systems that elevated individuals with specific knowledge and skills to leadership positions. The specialized roles we can identify from burial goods and settlement patterns suggest that these societies maintain detailed knowledge of astronomy, mathematics, engineering, agriculture, and environmental management. The fact that these specializations appear fully developed in the earliest sites indicates that the knowledge systems they represent were preserved through the catastrophe rather than developed afterward. The communication networks that connected these specialized communities across vast distances represent another remarkable achievement of post-Younger Dryas societies. Evidence of long-distance trade, resource sharing, and coordinated construction projects appears within centuries of the catastrophe, suggesting that survivor communities rapidly re-established contact and began coordinating their activities on continental scales. These networks weren't just economic or political, they served essential functions in knowledge preservation and transmission. Specialists from different regions could share information, compare techniques, and coordinate efforts to rebuild complex systems. The networks also provided redundancy that ensured knowledge preservation even if individual communities were destroyed or isolated. The artistic and symbolic systems that emerged during this period provide additional insight into the knowledge preservation networks that connected post-Younger Dryas societies. Similar artistic motifs, symbolic systems, and religious concepts appear worldwide during this timeframe, suggesting shared cultural frameworks that transcended regional differences. These shared symbolic systems weren't just decorative or religious. They encoded practical information about astronomical cycles, agricultural techniques, and social organization in forms that could be transmitted across language barriers and cultural differences. The consistency of these systems across vast distances indicates that they served as universal communication tools for preserving and sharing essential knowledge. The religious and ceremonial practices associated with these symbolic systems reveal another crucial function of post-Younger Dryas knowledge networks. Many of the ceremonies and rituals that we can reconstruct from archaeological evidence appear to have been designed as teaching tools, using symbolic narratives and practical demonstrations to transmit complex information to new generations. These educational systems were remarkably sophisticated, incorporating multiple learning modalities and built-in redundancy to ensure accurate transmission of critical knowledge. The combination of oral instruction, practical demonstration, symbolic encoding, and experiential learning created robust systems for maintaining complex information across many generations. The effectiveness of these educational systems is demonstrated by the consistency with which complex knowledge appears in archaeological sites across thousands of years and thousands of miles. The same mathematical relationships, astronomical alignments, and construction techniques appear in monuments built centuries apart by supposedly unrelated cultures, indicating that the knowledge transmission systems maintained remarkable accuracy over extended periods. But perhaps the most remarkable aspect of these post-Younger Dryas knowledge systems is their apparent focus on preparing for future catastrophes. Many of the monuments, information, storage systems, and social structures that emerged during this period seem designed not just for immediate survival and prosperity, but for long-term resilience in the face of recurring disasters. The astronomical knowledge preserved in megalithic monuments includes detailed information about celestial cycles that extend far beyond normal seasonal and annual patterns. Some sites track planetary alignments, stellar precession, and other long-term astronomical phenomena that suggest the builders were monitoring cosmic conditions on timescales of thousands or even tens of thousands of years. This long-term astronomical monitoring makes sense only if the builders understood that cosmic events pose recurring threats to planetary civilizations. The precision and persistence with which they tracked these cycles suggests that they were using astronomical knowledge to predict when dangerous conditions might return. The information preservation systems they developed were clearly designed with catastrophic survival in mind. Multiple redundant storage methods, robust transmission networks, and distributed specialist communities created systems that could maintain essential knowledge even if large portions of the network were destroyed. The Younger Dryas stands before us not as a distant academic curiosity, but as a mirror reflecting both our fragility and our extraordinary capacity for survival. In those 1,200 years of cosmic winter, our ancestors faced planetary devastation that would challenge even our modern technological civilization. Yet they didn't just survive. They preserved knowledge, rebuilt societies, and created monuments that still whisper their secrets across millennia. Their story reminds us that we live on a planet vulnerable to cosmic forces beyond our control, but also that human ingenuity and preparation can carry civilization through even the darkest catastrophes. As we face our own uncertain future under the stars, perhaps the greatest lesson of the Younger Dryas is this: we are the inheritors of survivors, and within us lies the same resilience that rebuilt the world from cosmic ashes.